I'm Jason Held from Sabre Astronautics, going to be chairing this session. We've got a few very interesting talks. Mark Sonter, Michael Della Locobo, Arun Rathan, Scott Dorrington, Tim Broadbent, and then we finished off with the glorious Andy Dexter. So I guess to start off, we're going to introduce Mark Sonter, who has had a great deal of depth in engineering experience in the mining industry and also increasingly in specifically asteroid mining. He describes himself as a grizzled but not grumpy engineer, so immediately we're kind of like doing that. Just a few highlights from his career. He started off as a high school teacher, then 6 years at university physics lecturer in Papua New Guinea, back 70 to 75, all the way up to mining engineering on the Olympic Dam and Beverley, nuclear engineering as well. And in '86 started Asteroid Enterprises, and he has been working that ever since and producing papers, working with deep space industries, and he is continuing to develop and publish on some of these concepts, and he's going to talk about some of that today. First talk is 20 minutes in total. He's going to get a warning at 12 minutes and then stop him at 15. Everybody else is going to get a warning at 10 minutes, and then we will stop you at 12. So about 3 to 5 minutes of time for questions. So why don't you go ahead and take it away, Mark.
I'm going to start by showing a whole bunch of pictures of different mining circumstances to remind people of how very different they can all be. There's a picture of the massive Kalgoorlie super pit in Western Australia, eating away into the city of Kalgoorlie Boulder. There's a much smaller open pit mine in Cobar, and you can see old turn of the century, previous century workings here, and an opening to an underground mine down there. Here's a much smaller mine. This is the Narwhal uranium mine up in the Northern Territory, 1979, mined out in 7 months, and the ore was processed over the next 10 years, sorry. The general idea of open pit mines is to chase the ore, and there is generally a problem of huge waste to ore ratios, and of course as they get deeper the waste to ore ratio gets worse. The planning depends on what is inevitably inadequate drill hole information, and was it Tim talked about that earlier today, I think. We need to understand our ore bodies, and here's an ore body. It's the prominent hill ore body. It's gone from being an open pit to not one but two underground mines, chasing the different levels of understanding of the ore. Underground, old school air leg miners, this sort of stuff still happens. The Kambalda story is an interesting one. The Discovery drill hole. This was a nickel sulfide discovery. Discovery drill hole was 28th of January 1966, and the first concentrate shipment from an underground mine, and the concentration plant was 18 months later. Almost unbelievably fast. Couldn't do it these days. Modern underground mines, we have these big stope drills that are automatic set up, or they're set up and then they automatically will drill an entire fan of blast holes without human intervention. The idea is to get the man out of the hazard area, or the woman. There are more women in underground mining as time goes on. This is a two-boom development jumbo for developing underground tunnels. Olympic Dam 1988, the beginning of the commercial scale operation of Olympic Dam, 50-ton haul truck, load haul dump, three-dimensional, massive stopes being the size of the large office blocks, or very large office blocks, 150 metres high, 40 metres by 40 metres cross-sectional area. And of course mines change. The shape of the mine changes over time as you mine up one area and you mine another area. This is the famous Olympic Dam, the biggest underground mine in Oz. Copper, uranium, silver and gold. I was involved in that early days. Saw it grow from nothing. You'll see an initial picture of it later on. This is the Beverley Field Leach Trial, 1998, pilot plant. Tiny little pilot plant. We didn't have licenses to operate it commercially, but it cost about $1 million to build. The entire EIS set of studies cost about $11 million, and if there had been a license, it would have been a virtually zero capex introduction for Heathgate Resources, which is owned by General Atomics, virtually capital-free entry into the uranium market. So mining can be very small as well as very large. There's the full-scale Beverley plant, still quite small. You can have dredge mining, that's on North Stradbroke Island where they're chasing heavy mineral sands. And the comparisons with terrestrial mining, best comparisons are not with large, low-grade, high-tonnage mines, but with remote, high-grade, high-margin, small throughput, very high-value product operations such as Papua New Guinea villages panning for gold used to flag down passing helicopters to take them to the bank, and I'm not making that up. Endermerker opal fields, they're one-man operations, mum and dad operations, quite rich if they strike it. Below gold fields in New Guinea, they flew everything in junkers. 8 2,000-tonne dredges in the 1920s to in the 1930 to 1940 period, the biggest airlift in the world. I look at that junkers flying over and I think of Falcon 9 heavies. Right. Diamond dredging. I'm just showing you the different sorts of mining operations. There are huge parallels between deep sea mining and asteroid stuff. Lessons for asteroid mining, mineralisation or what you want to reserve. These concepts are important. It's very non-trivial, the nature of the project definition, which I'll get onto in a minute. Do not choose between your options too soon. Progression of de-risking studies, scoping, pre-feasibility and bankable feasibility study, and the need to focus on CapEx reduction. Now I'm going to go back to what I originally wanted to talk about, but I wanted to show you pictures of mining, because we haven't had very many pictures of mining in the last day and a half, and I realised that my paper is pretty word heavy and picture short. So I want to talk about scoping studies and what I have done, both off my own bat and with DSI over the last couple of years. These are the asteroids and comets which we've visited. The number of near-Earth asteroids now discovered, as of a few days ago, approximately 16,000. When I first started looking into asteroid mining, near-Earth asteroids, there were 30 known near-Earth asteroids in the mid-70s. There were 380 when I started my thesis, and there's now 16,500 of these little buggers. About half of them are of the 100-metre plus size, and that's what I arbitrarily choose as being reasonable. Reasonable both in terms that we think that may be covered by regolith. As you get smaller and smaller, one presumes that you end up being bare monoliths, and reasonable in terms of being bright enough for a remote spacecraft going out to acquire it visually on the way back so that it can in fact find something to rendezvous with. Defining our asteroid project is non-trivial, as I mentioned a little earlier. How do we identify the targets we want to go to? What and how big and when is our market? Is our market for water, metal, storable fuels, silicon, PGM? No. Rare earths? No. Maybe much later. And to where? To Leo, Geo, Earth, Moon, L1, L2, Moon, highly elliptic, high Earth orbit for Mars departure. And the answer may well be all of the above, but in different ratios. We don't know yet. The market is still being developed, isn't it? Still embryonic. Mining method, beneficiation and processing, return propulsion and earth capture are all questions that have to be dissected out quite carefully. You don't jump to conclusions. Terrestrial mine project planning means choosing between competing mining methods and competing processing concepts to provide the desired production rate, to minimise capex and opex, and to minimise payback time, and to minimise project risk, and thereby maximise expectation net present value. And we have to do the same for any of our space mining projects, be they on Mars, or the Moon, or on asteroids. Notes from terrestrial mining. The purpose of my pictures earlier on was to remind you of the vast range of ore body sizes, types and geometries, and thus the vast range of mining methods and processing methods that we have to choose from. Open pit, underground, in situ, leach. You must understand your ore body and choose the correct mining and processing methods or risk project failure. And I've seen situations where it's come to project failure or close to project failure because people jumped to conclusions. Choice of mining plan and process flow sheet is often surprisingly difficult. The Olympic Yam Copper Uranium Gold project had 3 different alternative mining underground mining methods proposed in its original concept development and environmental impact statement, and 3 different metallurgical processes chosen for consideration. I, at the time, was the radiation and deeply involved with the ventilation planning, and I was able to say 2 of these 3 underground mining methods will be non-starters because the mine will end up being unventilated. Mulga Rock Uranium and Base Metals Project, similar, non-obvious mining, non-obvious processing. No one's bored. They've spent 10 years trying to work out, finally have cracked their process development. Beverley Uranium Institute Leach was seriously compromised because they did not understand their ore body, and thus left accidentally half of it behind. Northern Minerals is one of the clients that I'm working with at the moment. They were nearly bust. They were down to the last week of runway. They paid off all but the last half dozen workers. They were going to hand out the keys of the different company vehicles in lieu of redundancy packages, and they landed $35 million worth of investment from some rich Chinese. And a couple of weeks ago I was over there inspecting, looking at, helping with a little trial mine that they've got up and running, and they're building a trial processing plant, 1/10 scale model, with their $35 million, going to prove up their process. They're going to make some money out of that, which they make in the trial processing plant, and thus, what do you call it? Bootstrap themselves into the full-scale project. And that reminds me to remind you guys, the question has to be, how do we get into this at the minimum capex possible? So, in asteroid mining, we've got target-dependent choice of regolith models, and hence different applicable mining and processing technology. We've got concept-level choices we have to make in mass return, power and propulsion, processing at asteroid or delivery to markets and allowable mission time. It's horses for courses, and we will inevitably find ourselves flip-flopping between different design choices and different design decisions. Sophia was talking about mining and other people were talking about mining on Mars for water, and the choice was between buried ice and clays and permafrost. This choice between what is it we're trying to mine is something we're going to see time and time and time again, even when we know what commodities we're after. Terrestrial mining project pathways are always more or less like this. Desktop studies start when the board asks the exploration manager to go and look for a particular mineral somewhere in the world, and so they decide what the mineral is they're after. Is it going to be copper in Chile, or is it going to be coal in Kalimantan, or is it going to be gold in the Nevada Carlin Trend, or is it going to be copper in Mongolia, or is it going to be uranium in Saskatchewan? The board decides what commodity they're going to chase. The exploration manager says, here are the different prospective areas. The board says, we're not going to go there and there because sovereign risk is too high. Law and order is a problem. They identify the prospective areas, and within it select potential target areas. And within those target areas, select potential targets. Then theory and field work to identify that within that mineralised prospects. Then, having found a prospect, drilling out to find inferred mineral resource, then concept and scoping study, then metallurgical test work, then project planning and pre-feasibility studies, and finally, definitive feasibility study, funding and project go ahead, construct and commission. And hopefully, once it's constructed and commissioned, you find you've got a project that's more or less what you wanted, more or less works, and more or less on budget. Hopefully. So there's the study sequence. Desktop conceptual study, scoping study, pre-fees, final fees. A scoping study is the first pass at defining these things, and I've been working up a generic scoping, pre-scoping study. These are the sorts of contents pages that you see, and you can translate them directly across to asteroid mining. Flicking through, there are existence proof target lists. We know that good targets exist. I've been worrying about how to get robust estimations of mineral resources. Mining companies, exploration companies treat as a red letter day when they go to the stock exchange with their first statement of inferred mineral resource. How do we do this with something that we can't drill? I reckon I've got it cracked. I've generated a robust JORC-like asteroid resource estimate on hypothetical targets. I made up a hypothetical dark asteroid, said what sort of proportion likelihood it was of being a C or a D or a P or an X, put in example figures for likely water content in each case, and got that probabilistic cumulative distribution curve over on the right-hand side. And this was using an oil industry methodology, and if it was an oil industry situation and we got that green curve, we called it a discovery. There's a mining methods portfolio we've been looking at, and the RASOR is one that's been talked about: underground mole or cutter, solar bubble vaporizer, in situ hot gas rejected, reclaimed via ERE, electromagnetic regolith extractor, downhole pressure jet monitoring, in situ microwave. And we have to sieve these. You essentially do a SWOT analysis on each different alternative. So asteroid mining economics will be driven by CapEx, payback time, and net present value. What's the minimum viable project? Well, I showed you the minimum viable project for the Beverley deposit. There was the minimum viable project for Olympic Dam, $1 billion, right? And I showed you the full scale thing earlier on, and that was 1988. What does it all mean? We've got approximately 50% of these 16,000 NEAs are big enough to grow and retain mineable regolith and to be visually acquired. Of these known 7,500 and identified 1,400 or so significantly more accessible than the Moon. Of these 1,400, about 10 to 20% give intermittent very low returns. And of these known 200 or so, statistically 50% are dark and thus potentially water and volatiles. 50% is a highly prospective number compared with 1 in 1,000 terrestrial. Can we close the business case? We need positive net present value, we need to minimise CapEx and OpEx, we need to minimise payback time, we need to meet acceptable price points. Only the feasibility study can tell us this. First we have to do the concept scoping study, and that's where we got to as of several months ago. Ta-da!
Great. All right. So we got about 4 minutes for questions. Really good. Any questions for Mark?
Just the mining system that you mentioned, ERE, what is that?
It's a proprietary Deep Space Industries electromagnetic excavator. Right? A lot of this material is magnetic, and so we have been investigating whether we can use its magnetic properties to dig it. Suck it up, vacuum it. It's a working vacuum machine.
Any other questions?
How much do people actually study the difficulty of operating it? I mean, there's no gravity. How do you tether to the object? What's the standard for doing that?
Tim, that's a very good question. It is, Tim, isn't it?
It's Ian.
As with the mining and as with the processing, you have to start by making up a portfolio of possible technologies, and then you sieve them by means of the mass constraints and the power constraints and how likely they are to be workable. You've got to do on Earth testing of your different anchoring mechanisms. But you've got to start by having a portfolio of the different possible technologies. One way with such small objects might be to tie a rope around the whole damn object, or a net around the whole damn object.
Okay. Any other questions? All right. Thank you very much. Goodbye. Okay.